Hello guys, welcome back. In this video, we're gonna start learning about text analytics in R. And we'll start with string operations so that we can know how to extract the information of interest from enormous irrelevant text. And to use string operations in R efficiently, we'll also learn the language of regular expressions. It is a language independent of R and can generally be used with any language for string operations. Let's start with this motivating example. Since his 2016 presidential campaign started, Donald Trump has sent thousands of tweets into the world. They've consumed news cycles, antagonized opponents, and riled up supporters. Because Trump has used Twitter to such great effect, and because his tweets are a useful time capsule for his campaign. By analyzing his tweets, we can see what Trump talked about most, which people suffered the majority of his attacks, and how Twitter reacted to what he was tweeting about. To do so, we need to first collect Trump's tweets from Twitter. But even with the tweet data, it could be a mess and lack variables that are critical for answering the questions we are interested. For example, we may want to know how Trump's most formidable rivals changed as the campaign went by, and create an informative and aesthetic graphic to show it. The simplest way to do so is to identify candidates' names from these tweets and count the number of times they are mentioned. But there are tons of tweets. It is nearly impossible to read individual tweets and pick out those names by eye. Then, how can we instruct computers to search text? This is why we need to know string operations. So, why do we care about strings, or more generally text? Nowadays, a lot of interesting data out there is in character form. Interesting data sources include web pages, emails, surveys, logs, search queries, and so on. Even if we just care about numbers eventually, we'll need to understand how to get numbers from text. Besides, strings also play a big role in many data cleansing and preparation tasks. So let's start. In R, strings are just the sequences of characters. But different from other languages, strings in R are atomic values, which implies that we cannot use indexing with a string. To create a string, just use double quotes or single quotes and type anything in between. We can create strings with either form of quote mark. Unlike other languages, there is no difference in behavior. What are created are called string literals, which are evaluates to a character type. Either form of quote mark may be used to escape the other. As in this string, it means double quoted strings can contain single quotes and vice versa. But I recommend always using double quotes because then we can use apostrophes. What if we have to use double quotes literally in a double quoted string, as in this string? Then just use backslashes to escape their special behaviors for string construction. Then we can use double or single quote marks literally. When printing a string literal in R, the interpreter will display all characters exactly. Note that If you want to include a literal backslash, you'll need to double it up. That is because backslash is itself a character of special use. So we need to use another backslash before it to escape its special behavior. Beware that the printed representation of a string is not the same as string itself, because the printed representation shows the escapes. If we want to display the raw contents, use write_lines. Then all these character sequences will be translated into what they actually represent. There are a handful of special characters. One type of them are white space characters. That is, characters that represent horizontal or vertical space. They count as characters and can be included in strings. The most common ones are space, new line, and tab. And you can see the complete list by requesting help on these two commands. We can use the asCharacter function to convert values of other types into strings. And from a string, we can also use other coercion functions to create a value of the corresponding type, as long as the conversion is sensible. Although strings do play a big role in many data analytics tasks, they are not glamorous, high-profile components of R. Base R contains many functions to work with strings, but they can be inconsistent, which makes them hard to learn and remember. Additionally, base R string operations lag behind their counterparts in other programming languages, so that some things that are easy to do in languages like Python are rather hard to do in R. So instead, we'll use string functions from string R. The string R package provides a cohesive set of functions designed to make working with strings as easy as possible. Functions from string R have more intuitive names and interfaces. For instance, all function names start with this prefix, and all functions take a vector of strings as a first argument. String R simplifies string operations by eliminating options we don't need most of the time. And it is a package in the core tidyverse and works well in conjunction with the pipe operator. Here is a list of string operations provided by string R. Generally speaking, these functions can be grouped into 4 main families. Most of them have straightforward uses. And in this course, we'll focus on the first 2 groups of functions because they are more useful, but have a slightly steeper learning curve, thereby worth being discussed further with examples. Let's start with some basic things. That is, how to count the number of characters in a string. If we apply the length function to a string, it returns 1, which means this is a character vector of length 1. So how can we count the number of characters in a string? To do so, we need to use string length from string R or nchar from base R. The string length function can vectorize. It can work with a whole character vector and return the number of characters for each element in this character vector. To combine 2 or more strings, we can use string C, short for string combine. This function defaults to have no separator, but we can further use the separator option to control how they are separated in the resulting string. String C also vectorizes, but if you want to combine different elements of a character vector into a big string, you need to use the collapse option. We can extract parts of the string using string sub. It takes the start and end arguments, which gives the position of the substring to be extracted. Note that string sub won't fail if the string is too short. It will just return as much as possible. Because strings are atomic values in R, we cannot modify characters in a string directly. To modify strings, we need to use the assignment form of the string sub function. In this example, we first use string sub to extract the first letters of the three strings, convert them into the lowercase form, and substitute them for the original capital letters. Before moving forward, let's first consider an example of text processing, setting a stage for more advanced tool for string operations. This plain text file contains the transcript of Trump's nomination acceptance speech in the 2016 Republican Convention. ReadLines is a function contained in readr, the data loading piece in the tidyverse, calling it to read the text in this file line by line. It returns a character vector of many lines. Then we can use string C to combine these lines to make one long string, and use string sub to display dozens of characters in the very beginning. To perform text analytics, we usually need to split up the text into some form of constituents for subsequent analysis. Let's use string split to split this long string into pieces. The string split function can work with vectors, and because each element of a vector might contain a different number of pieces, this function returns a list. And because the input character vector contains only a single string, the resulting list has only one element. And our most basic tool for summarizing text is word counts. It can be produced using the table function. The output of the table function is a named vector containing unique words and their count of occurrences. And the words are the names of the vector elements. And all the elements are sorted alphabetically by name. Notice that some names include punctuation marks. For example, again with a comma, this again with a period, and this again has a capital start letter. And they are treated as separate words. But in fact, they are not distinct words. So this is not ideal. While simple splits are effective in isolating fields, when we want to look into the result a little more deeply, we see that we need something more elaborate. Another example is the text of an email. It contains many types of pieces. Then, how could we match a phone number, an email address, a URL, and many others? Each of these types of data have a very regular pattern that we can easily pick out by eye. But how can we pick them programmatically? This gives rise to the need for a pattern language, which can help us better search text. What we need are regular expressions. A regular expression, or regex or regex for short, is a special text string for describing patterns in strings. Regular expressions are a very terse language. They take a little while to get your head around, but once you understand them, you'll find them extremely useful. The simplest pattern matched by a regular expression is a literal character, or a sequence of literal characters that match themselves in a target string. For example, fly matches superfly, and fly in this phrase. But it does not match this plural form in these two phrases. What if we want to match both the singular and plural forms of fly? If we want to make our regular expressions more versatile and general, there are a few special characters called meta characters that we can use to construct more complex patterns. These meta characters have special meanings for pattern matching and allow us to indicate alternative, positioning, grouping, and repetition. One example that you may find familiar is the vertical bar, indicating alternatives. Connecting these two literal sequences tries to match fly or flies. And the concatenation of regular expressions is also a regular expression and allows us to match longer patterns. And parentheses here define groups, determining the scope of these two logicals. On the next several slides, we start with very simple regular expressions and then gradually get more and more complicated. Once you've mastered pattern matching, you'll know how to apply those ideas with various string R functions. To know regular expressions, we'll use string view and string view all. These functions take a character vector and a regular expression and show you how they match. Many string R functions come in pairs. One function works with a single match, and the other works with all matches. And the function working with all matches will have the suffix all. As you can see, matched parts are highlighted in the target strings. One remark here is that matches never overlap. For example, in this string, this regular expression won't match this substring because it has some parts overlapping with the former and the latter matched substrings. Next, I will introduce several types of meta characters that we can use to construct more complex patterns. In regular expressions, there are a number of tools used for matching more than one character. One of them is character classes defined by square braces. Square braces are also used for grouping, but they groups a class of characters that we want to match for one character position. In other words, These characters are alternatives to one another for a character position in a target string. So the capital AEIOU enclosed in square braces matches I and O in this course code. And 789 enclosed in square braces matches 9 in this course code. A dash inside square braces denotes a range. So this regular expression matches a two-character string starting with a capital letter followed by a digit. A caret inside the square braces negates what follows. So this expression tries to match anything but a digit. And a period means matching any character except a new line. Regular expressions provide several predefined character classes. Here is a list of them. And there are two flavors of predefined character classes. One uses a pair of colons around a predefined name inside square braces. And the other uses backslash and a special character. They are sometimes interchangeable. In this example, I use the predefined character class for punctuation characters so as to avoid typing a variety of punctuation marks. The next step up in power involves controlling how many times a pattern matches. And the meta characters used for this purpose is called quantifiers. They include the plus sign means one or more times. The asterisk means 0 or more times. The question mark means 0 or 1 time. We can also specify the number of matches exactly by using curly braces around a number. And this notation can be extended by including a comma, meaning n or more times. We can further specify an exact upper limit with this notation. By default, a quantifier applies to the last character, but we can use parentheses to have it apply to a whole group, as shown in this example. So a pattern defined by these two characters is required to repeat at least twice in the target strings. But if a meta character has a special meaning, how do we match it literally? What we need is an escape to tell the regular expression we want to match it exactly, not use its special behavior. Like strings, regular expressions use the backslash to escape special behavior. However, backslash is also used as an escape symbol in strings. When we use strings to represent regular expressions, backslash is also used as an escape symbol in strings. So to create the regular expression to match special characters exactly, we need a double backslash up. So in this example, the first backslash escape the special meaning of the second backslash in this string, so as to create a regular expression that match the left square brace exactly. Then, if backslash is used as an escape character in regular expressions, how do we match a literal backslash? Well, we need to escape it, creating the regular expression in this form. And to create that regular expression, we need to use a string which also needs to escape backslash. That means to match a literal backslash, we need 4 backslashes to match 1. By default, regular expressions will match any part of a string. It's often useful to anchor the regular expression so that it matches from the start or end of the string. For this purpose, we can use a caret to match the start of the string and the $sign to indicate matching the end of the string. So the pattern expressed by this regular expression only matches tags and the start and end of a string. Earlier, we learned about parentheses as a way to disambiguate complex expressions. Parentheses also create a numbered capturing group. A capturing group stores the part of the string matched by the part of the regular expression inside the parentheses. Then, we can refer to the same text as previously matched by a capturing group with back references, like \1, \2, and so on, to form a more complex pattern. For example, this regular expression expresses a pattern that finds all pairs of repeated characters. This is because the regular expression inside the parentheses will match a non-new line character and number the resulting capturing group 1. Then, we use this back reference to require a duplicate to follow this capturing group. So this entire regular expression matches pairs of repeated characters. And this expression finds all quadruples of the ABBA pattern because the two back references swap the positions of the two capturing groups. And an important use of capturing groups and back references is parsing HTML tags, as shown in this example. Now, we've learned the basics of regular expressions. It's time to learn how to apply them to real problems with a wide array of string R functions. Let's first consider how to split a string based on a match. In this example, instead of a simple space, we compose a regular expression that matches any number of punctuation marks and a white space character. And we end up with a much better result than our previous attempt. But you may wonder why this period hasn't been removed. The reason is that there's no split having occurred at the end of this line. So the splitting pattern hasn't been applied to the very end of this line. We need other tools to remove this period. Instead of splitting up strings by patterns, we can also split up a string by character, line, sentence, and word with a boundary function, as shown in these examples. To determine if a character vector matches a pattern, we can use string detect. It returns a logical vector the same length as the input. And we can further pipe this logical vector forward into the sum function to determine the number of matches in this vector. And rather than a simple yes or no, we can use string count to figure out how many matches there are in a string. And it vectorizes and tells us the number of matches in individual strings. We can use the output of the detect function in an indexing operation to select all matched strings. And this string subset wrapper makes it even easier. To find the positions of matches, we can use these two functions. String locate and string locate all give us the starting and ending positions of a match, and the result is organized in a matrix. A common use pattern is that we first use string locate to find locations of the actual text of a match, and then use string sub to extract or modify it. There are also functions that allow us to extract the text of a match directly. Use string extract to extract the first match, or use extract all to get all matches. The string extract all function returns a list because different vector elements may have different numbers of matches. And string match and string match all have a similar use. The main difference is that the extract functions only give us the complete text of a match, while in addition to the complete match, these match functions also give each individual component of a match. Please try these two functions in RStudio to see the difference. There are also functions that allow us to modify the text of a match directly. String replace and string replace all allow us to replace matches with new strings. The simplest use is to replace a match with a fixed string. For example, all vowels in these three strings are replaced by hyphen. String replace all can also take a vector of named patterns and perform multiple replacements all at once. In this example, this indicates every English numerals to be replaced by its corresponding Arabic numerals. Instead of replacing with a fixed string, we can use back references to insert components of a match. In this example, this regular expression matches the first three contiguous space-separated substrings and results in three capturing groups. And the substitute is also specified by a regular expression that contains back references. As a result, it exchanges the positions of the second and third substrings of the match. Take the first line as an example. The original order is friends, delegates, and fellow Americans. Now it changes to friends and delegates. So the positions of the second and the third substrings have been exchanged. And the string R function can work smoothly with dplyr verbs when our data wrangling process involves text processing. Given a table of a tweet dataset, we can use string extract all to extract all hashtags. Use string count to count the number of hashtags. Use string extract all again to extract all URLs, and use string count again to count the number of URLs. But we will have two list colons in the result, because Each call to the extract_all function returns a list, and the returned list is nested in a cell of the corresponding columns. When we have a list column, we can use unnest to make each element of the list have its own row. In the first example, all hash tags nested in a cell are spread into their own rows, with values in the other columns duplicated accordingly. And in the second example, all URLs nested in a cell are spread into their own rows instead. Another noteworthy function that works with regular expressions is extract in tidyr. Given a regular expression with capturing groups, extract separates the substrings stored in these groups and turns them into their own columns. In this example, this regular expression matches values from the second row through the fourth row, produces two capturing groups for each matched value, and turns each group into its own column. Well, this is all I'd like to introduce for string operations. In our next video, we'll learn how to scrape textual data from the web.